Hey guys, welcome back to my continuing attempts to use a vintage Hewlett-Packard spectrum analyzer and tracking generator to align a vintage TV. When we last left off, we got some inklings of a response curve on spectrum analyzer. What I was really waiting on though is this attenuator, which has arrived, and it is a beautiful thing. Not much to it. On the outside we have two BNC connectors, one on either side, and an odd looking rotary switch. It doesn't matter which is the input or output, bidirectional. Inside of this, it's a stepped attenuator. It's a rotary switch that switches in different resistor combinations to cut the signal by 10 dB, 20 dB, 30 dB, 40 dB, all the way up to 120. And that's great because this goes in steps of 10 dB, and the variable control, output control on this is variable 10 dB. So between the two of them, you can cover a vast range with a decent level of precision. So the issue was the output on the tracking generator is much too strong to inject directly into a sensitive circuit. So the output of the tracking generator now going into this, and we can cut it down, and as you'll see in a moment, I can cut this down by 100 dB and still get a readout of this, even which is one stage of amplification. Alright, now the other issue I had was my lead dress. I just had some alligator clips and nothing was shielded, and we were getting a lot of noise and distortion. So I took the output of this BNC cable, and at the end of it I took a BNC connector and did a couple things. I put a resistor right from the center to the body of this barrel here to terminate it. Ideally it'd be 50 ohms non-inductive resistance. Right now I just tacked in a 47 ohm resistor. I'll have to order one up. And then it's not ideal, but for now, just to make sure this works, I soldered in two short lengths of wire and went right to this connector. I'll rig up some little baby alligator clips. And then there is the spectrum analyzer probe. So this is where we're injecting signal. I'm going right to the grid of this tube. But having some trouble figuring out where exactly should I connect this. I can't connect it after the detector because we need to look at the RF. We can't look at it after it's been rectified and filtered. But on this particular stage, it turns out that is a little tricky to do. Well, first let me show you how I had it hooked up in our last video and how I'll hook it up right now. So here is our detector, half a 12 AT7. It's rigged up as a diode with the grid going to the plate. I'm injecting a signal on pin 1 of this tube, and I want to look at the output. Now I can't go to the plate of this tube because what I'm adjusting at this stage is this. We have two variable coils and a variable cap, and I want to see what does that do to the frequency. So where I've been probing is the output of that, which is pin 3 of the cathode of this tube. And so I'm injecting over here. I'm looking at the signal over here. That's a problem. I'll show you back at spectrum analyzer. I really need to set up some presets on this because every time you turn this off and turn it back on, it goes into default mode, which scans 0 to 1500 megahertz, and it doesn't have all the settings I was last using, so I'm having to do this again and again and again. But you can save a bunch of presets and then recall them, I think 5 or something like that, to remember your settings you last used. I definitely want to do this for some of the common stuff I work on. Well, anyways, so center frequency 24 megahertz, frequency span 10 megahertz. Alrighty. Now, let me see. I also do not have it rigged up, so I am fixing the AGC at minus 1.5 volts as indicated in the alignment instructions. Now something else, when I was previously did this, I was in logarithmic scale mode, which means going from this noise floor here up to the top is a vast range of amplitudes. We should really be in linear mode, and luckily we can do that with this. However, it does introduce an offset with the reference level, and I need to, like, the signal is now off the bottom of the screen because it's added this offset. We need to get this all the way down to 0. And you can start seeing a trace on there. Now I need to play around with the injection levels. I should finally start seeing something. Almost. Oh geez, am I going? Alright, now I'll finally start doing it. Alright, now level. Let's increase the injection signal level. So I'm thinking, okay, cool, we're seeing a response curve. Centered at 24 megahertz as they indicate, frequency span 10 megahertz, we got a nice response curve. If I start tweaking coils, it's going to start moving a little bit. However, that's nothing like what it's supposed to look like. It's supposed to have a double hump with 2 key frequencies. And as I mentioned in the previous video, it's inverted. We just pretend we're looking at that. That's not what we see. I struggle around with changing, oh, maybe I'm instructing too strong a signal, let's cut that down. But I just couldn't get it right, so just sheer coincidence. I was trying to move my probe to different points in the circuit, and I noticed when I disconnected it from anything and just left it in the general area of that circuit, and increased my input a bit, I got a double hump response. And those 2 humps are pretty darn close to where they're supposed to be. So, what's happening? I was thinking about this a little bit. Let's look at where I was trying to hook the probe. Remember I mentioned about this probe being an active probe. It's 10 mega ohm input impedance. It's like putting a 10 meg resistor from the point you're testing to ground. It also has capacitance though, about 10 picofarads. So when I'm probing at this point, I'm adding a 10 picofarad capacitor from this point to ground, which means it's in parallel with this coil, which is one of the things I'm trying to adjust. We're working with high frequencies. 10 picofarad matters. That's going to act like a filter on this, with the resonance. If I put an inductor and a capacitor in parallel with it, we cannot do that. So, I have to just sort of gimmick this and just lay the probe near the circuit and put a strong enough signal in that I get a readout. The problem with that is, it's just sitting there, and if I just move the probe slightly, it drastically changes the image. Now this is the last stage. When we go back further in the stages, I can connect the probe to the output of the previous stage. In other words, a point that is lower impedance and less affected by me clipping a probe into it. But for this particular point in the circuit, for this particular stage, the way I'm injecting and trying to read the output, even with this active probe, it's still affecting the circuit too much. And there's really not much I can do about it other than trying to put this probe in a position that's stable enough that I can see something. So the more I'm playing around with this, the more I'm realizing, yeah, it's cool, and in some circumstances you can do amazing things, but it's not for everything. It's not going to work in all circumstances. Now the other thing I've been trying to do is it got me thinking that, hey, why don't I hook the scope up to it too in XY mode? In other words, why I should be able to do both at the same time, see it both on the spectrum analyzer and on the scope, and I'll connect the scope up where they suggest to when doing a more traditional alignment technique. So I have my scope set up that way. And the one thing I'm lacking is the horizontal sweep drive for it. I need to see if there's a sweep output from the spectrum analyzer or tracking generator. It's probably in the back of the tracking generator, because with that I should be able to. But even so, there's that same curve, and on the scope it is pointing in the right direction. You know, it's pointing down like they show in the service info. It's just a little unstable because I'm not locking onto the same sweep rate as the alignment generator. Actually, I can invert this so that everything looks the same. Huh, I guess you can't invert channel 1, or at least I'm not figuring out how to do it. But I know I can invert channel 2, so let's just switch to that. Channel 1 off. Alright, cool. But this is great because we're essentially seeing the same thing there as over here, which verifies this is a valid response. I'm not tricking myself. I was discussing my setup with a colleague, and he gave me some really good advice that I regret not thinking of on my own. So to go over the situation again, I was trying to probe at this point, which puts this probe in parallel with a coil, and it results in me getting a very misleading response curve where it's showing a very strong peak at this point. I'm pretty sure it's the resonance of my probe's capacitance in parallel with that coil, and it's nothing like what I should be getting. So what I then did is I disconnected the probe from the circuit entirely and just sort of laid it down. So not physically connecting that probe tip to anything, and just nestling it in this area. And if I put a stronger signal into the set, hey, I get my double hump response. Couple problems with this. One, I'm putting in a pretty strong signal, much stronger than I want to. And two, if I just move this probe around a little bit, it wildly affects the display. That's no good. So he said, hey, decouple the probe. If you recall, the alignment instructions for hooking up the scope say to put a 100K resistor in series with your probe tip and the circuit. I can do the same thing with this. Add a high resistance resistor between the probe tip and the circuit. So I'm going to put a 1 meg resistor on the tip of that probe, and then connect the end of that resistor to the point in the circuit I'm interested in. Let's see what that does. Alright, so with that 1 meg resistor connected to the end of the probe tip, and now I use the end of that resistor as my probe, and we'll go right into that circuit point. And there's my double hump response. And it's not going to be affected as I move things around. I can physically connect those two securely together. It's not affecting the circuit, and I can still get an accurate response curve. So that's what I'm going to do. Okay, we are finally ready to start the alignment. I want to use as small an input as I can and still see a good response curve. Now, starting with the first step, our challenge is to get this. We want to peak at 21.6 and 25.9. Now, as far as markers go, I can program one directly, then the other one's going to be an offset. So if we do marker normal, I can dial in 21.6. For the second one, I need to know what the delta is. So if we subtract 21.6 from 25.9, we get 4.3. So when I do delta of 4.3, and it's over here. So we want to have two peaks of equal amplitude. We do not. That is our challenge. And to do that, we are adjusting A1, A2, and A3 as indicated. What are those and where are those? Well, I have the chassis propped up at a bit of an angle here so I can both get my probes under there and get at the stuff I need to adjust, which is these. Those are the two adjustment coils, A1 and A2, and then A3 is a variable cap. This is the tube I'm injecting a signal into right now. So I'm going to be tweaking these three to achieve my goals. And I say that A3 is the one that has a bigger effect on where that second peak is. So I'm going to try to adjust that. Now, what do I mean by adjust? Don't use a metal screwdriver. You need to use a plastic tool with a metal shim on the end. These are slotted, threaded shafts. You fit this in there and rotate it as such. And as you rotate it, you look on the screen. And if you look closely, that peak on the right is sliding over to where I now have the peak basically on that dot. But now the two peaks are not equal amplitude, so let's try tweaking A1 and A2. See what that does. Okay, well, that shifts the whole thing over to the left. Or the other way. Okay, now we're getting our peaks to be pretty darn equal, but they're not on dots anymore, are they? No. So here's where you have the fun, and you go back and forth and back and forth and back and forth, being those three controls to get what to achieve your goals. Also kind of screwy the way this goes when you're in delta mode, the two dots just float in there wherever you left them. Okay, cool, now we're back the other way. We got a peak on the right, but now the left is way too low. So we go back to, this is where you go back and forth. Eventually, some patience, you can get this to go. Trying to use a camera while you're doing it just adds an extra dimension of fun. This actually isn't too bad. I mean, I can see as I'm slowly going back and forth, I'm honing it in to where I want to be. So I will keep at it. I think you get the idea. I'm going to jump around between those three adjustments until I get two peaks where those two dots are. Alright, I think that is pretty darn good. We have the peaks at the dots, and they are very similar in amplitude. Alright, let's move on to the next step. Now we're going to be injecting V5, which is the second video amp. So we just did the third video IF, and we did this circuit. Now we're going to do the second video and adjust A4. Moving on to the next stage now, we're supposed to have a peak at 25.3, and it looks something like that. Remember, we need to invert it in our minds. So the overall shape isn't too bad, but there's my 25.3 megahertz marker. We got a peak way over here. So that definitely needs some tweaking. And what are we going to tweak? This guy right here. And people get frustrated sometimes and they say, oh, I can't see exactly what you were doing or where you hook things up. Unless you have this exact set with this exact equipment, the details are not important. It's the overall procedure. You inject it at a certain point, you measure at a certain point, you adjust the right coil. It's going to be different for every single set. But the concepts are the important thing. So I'm tweaking that coil slug, I'm walking it over, I want to get my peak on that dot, and there we go. Right there. And the shape is very similar. It has kind of that odd kick out there. Now I did change my sweep width a little bit because it was so off at first I couldn't find it. So let's put that frequency span back from 20 to 10 megahertz. Now it looks even more like the picture. Oh, I can also see that when I decreased my sweep range, it made it a little more accurate. And I can see I'm a little off a bit. That's why you want to use the minimum sweep range possible to see the important details. Oh yeah. Alrighty, onwards and upwards. A few more steps to go through. I finished aligning the video IF using the spectrum analyzer technique, and I followed the SAM's photo fact. Now, the Zenith factory alignment instructions are actually the same, in that you inject the signal on the grid of the preceding stage and then you align it. So when I aligned the third stage, I injected into third IF tube, and I aligned the second stage, the second IF tube, and for the first IF stage, the first IF tube. Now, I want to double check the overall response. To do that, you use the technique I mentioned earlier where you inject it by putting a jig over the mixer tube, basically a shield that's ungrounded, and it will get coupled into the tube internal elements and then go through the entire system. But to do that, I'm going to do a more conventional setup with a sweep generator. I'll use the 8662A back there, and an oscilloscope in XY mode. But not that scope. As I mentioned earlier, the markers aren't showing up on that. There is an output on the sweep generator that's supposed to go to the intensity modulation on the scope, and so the markers show up as bright dots. My scope isn't working for some reason. I'll dig up a different scope or XY monitor. I want to do that to double check, hey, does the spectrum analyzer technique give me as good a results as it seemed to, looking on the display of the spectrum analyzer. But also right now, let's see, what does it actually look like on the TV? There's one shortcoming of the spectrum analyzer, is that you can only do one exact marker, and then you can use the delta offset to sort of do a second marker, but that's it. That's as good as it gets. Well, that's looking a whole lot better. So right away, we're not seeing that weird screen window effect we saw earlier. Also, we're seeing a very distinct pattern of dots in different areas. That is chroma dot, chroma crawl. It's the color information. So this must be a color cartoon that I'm feeding into the set. These early sets, the sets from the 40s, the higher end sets, had full video bandwidth of about 4 megahertz. Later on, when color came out, they put the color burst at 3.58 or 3.579, whatever, and then some phase modulated color info, and they limited the video bandwidth so you wouldn't see that getting into the image on a black and white set. However, these earlier sets were done pre-color, so seeing that means the bandwidth on this has got to be better than 3.5 megahertz, and that is great. Also, I gotta say, it's looking pretty darn good too. I did tweak the magnet a little bit around the neck to get, and I played around with the centering controls to fill it out. Looks like we need to come this way a little bit. The set does have horizontal and vertical centering controls, which is nice. So there we go. Now I can also put this in multi-burst bar sweep mode, which will give us a pretty good indication. Holy crap, yeah, that's outstanding. So each one of these sections corresponds to a burst of frequency, the highest one being 4.5. And we're seeing detail out at 4.5, which means we've got a really, really good video bandwidth. You can turn these on and off. So yeah, that's the 4.5. I am seeing distinct vertical stripes at 4.5. This is 4, 3.5, etc. So typically when I do this, especially on lower end sets, the lines start getting indistinct here. And forget about it going this way. It's just gray. You don't even see those vertical stripes. So that is outstanding. Now I'm going through the full tuner right now, which means the tuner alignment must be pretty darn good too. I also got to say these Zenith engineers did a really good job with their sweep circuits, because aside from some slight twisting at the top, those are really clean vertical lines. There's no twisting or anything. A little bit of odd interference here, but that could just be kind of an optical illusion. I don't know. Tweak the fine tuning a little bit. Alright, now, as I said, next up we're going to check the overall response, even though from looking at this it looks pretty darn good, but maybe we can tweak it slightly, and then we'll do the sound alignment. Something else I wanted to point out, I've got color bars up on the screen now. And if you look close, the dot pattern is slightly different in each one of these vertical bars. They're different colors. Some of you may know about some Doctor Who episodes from the 70s featuring John Pertwee as the Doctor that were recorded on videotape, and the color copies were lost or recorded over, but black and white copies remained. They were able to take them and, using that dot pattern, colorize them accurately. Yes, it's a PAL system versus NTSC, but that same or similar type of dot pattern effect also happens in the PAL system. So what can you do about that? Now, it's not really distracting if you're far away, but up close it can be a little annoying. What if I want to watch some programming and not see those dots? What do you do about it? 1, watch black and white programming. 2, get rid of it. In particular, something I've been meaning to try out for a long time, I have an ATSC over-the-air converter box that has RGB outputs, separate composite outputs for red, green, and blue signals. The green has the luminance info, meaning it's analogous to, or basically it's the black and white picture info, the brightness info. So we can forget about the red and the blue and just take that green and feed that into an RF modulator. The RGB component outputs don't have the color burst. They don't have the phase modulated info. They're just intensity for each of the different colors. The human eye is most sensitive to green, so they give the most bandwidth content to the green signal. And that is all you need to reproduce a great looking black and white signal, and it won't have those color dots in it. So we'll experiment with that coming up soon, especially now that I have a set where it's very, very noticeable and distinct and easy to illustrate when they're there and when they're not there.